So, very good morning to you all, and I welcome you to today's session. So today, yesterday we discussed about how do we like some simple processing steps on an raster, like how do we resample an image, and then how do we reproject image, or then how do we clip or subset an image. So today we will discuss more about some other processing steps that generally are involved in geoprocessing. So first we will talk about mosaicing images. So what is mosaicing means, first of all? So mosaicing is, when you say mosaic is a combination or merge of the two or more images. So for example, if you take the example here, so suppose we have, so now suppose that we have these images which are covering the different spatial extents. So but they may be overlapping in certain areas and so on. So by suppose we want to combine all these images together, like suppose this blue image is covering this portion of this is the entire area, and the blue image is just covering this area, this portion of these extents of this entire image, and this is this is covering this portion of these total extents. So now suppose if we wanted to create a seamless single image by combining all these images together, so that is what is called mosaicing. So once we mosaic all these images, so some areas may be overlapping. So in the overlapping area, we may want to like calculate the average, or maybe like maximum intensity and so on. So there will be different operations. So when we combine these all images together, so this image looks like this. So this is what we call mosaicing. Mosaicing means combining or merging two or more images which may have similar or different spatial extents. So now let us see how do we mosaic the images together. So anyway, as usual, so first of all we will be importing all our required libraries like OSGeo, Matplotlib and NumPy. NumPy also may be required later on. So apart from mosaicing, today we will be covering upon like how do we do some local analysis on the image. Local analysis in the terms like the operations, whatever, or operation or processing what we are doing, that will be applied to individual pixel. So then later on we will discuss about the global analysis. So in case of global analysis, the operation will be done on the entire image instead of applying it on an individual pixel. So after this we will discuss about like different DEM processing, like if you have digital elevation model available of certain area, then we'll see that how do we create a hill shade, or you just if you want to calculate slope from the DEM or aspect from the DEM. So these operations we will cover in the subsequent sections. So to start with mosaicing, so first thing, like we will be, as usual, we will import all our required libraries like operating system. This is for changing the working directory. Then OSGeo GDAL, then Matplotlib for plotting, and NumPy array for if you want to do some processing on the data. So first thing, I am changing my working directory to be the directory where I have different images. So now in this folder, NRMS Nainital Mosaics, I have so here I have these 4 images. So these are covering the different spatial extents. So we will see that how can we combine them together to create a single big mosaic of images. So first, in a list I have stored the names of all these variables, like these are the file names which we will be mosaicing together. So these are now, right now we are just demonstrating with a single band image. So later on, once you learn this, you can combine all multi-band images as well. So in this file names, I am just storing the names of all the files which I will be mosaicing together. So like these are the L3NH44 G4-09650 21st February 18 band 2 TIFF. So this is the band 2 image of list 3 sensor of resources to spacecraft. So this is some area somewhere in Uttarakhand. So now let us see how these images look like, how they are different, and then later on we will combine them together to make a single big mosaic. So first I am storing the names of file in a list. So like these all images I will be reading one by one, and the data set, like once we read an image using JIDAL, so it will return a data set. So all these data sets I am storing in another list. So like here DSS list I am creating just an empty list. So then later on for file in file names, so I am iterating over all the file names one by one. Then jidal.open, with jidal.open I am opening that file for reading. Then I am appending that data set to my ds_list data set. So now my ds_list data set will have 4 data sets. So now let us visualize that how these individual images look like. So here again just I am creating a figure of 10 by 10 size, then iterating over that ds list. So for I in range 1 to len ds list plus 1, then I am just creating a plot with 4 subplots that are arranged in 2 rows and 2 columns. Then again I am calling this plt.imshow function and fetching one by one the data sets from the ds_list and read as array and just displaying the images together. So these 4 images look like this. So this is some area, then like this portion of river, you can see this is coming this area, and like this maybe some other portion, or like these two may be coming together. So these are the 4 different images. Now let us see how do we combine these or create a mosaic of these 4 images. So for this we will be using, actually you can do without using this utility also, but for this purpose we will be using a utility or called jidal.warp. So either like you can JIDAL warp is a very versatile utility. Actually JIDAL warp you can use for multiple purposes like reprojection or you can say rescaling or resampling, or you can use for mosaicing as well. So that is how do we do, by using jidal.warp. So here I have done jidal.warp. Then next first argument to this warp function is the destination file name, to which file you want to save the data. So mosaic. So right now I am giving it name like mosaic_image.tif. Then the second argument should be the names of files, or you can say the list of the files which you want to mosaic together, or maybe the data set. So the second argument can be like, if I see the help on this jidal.warp function. So you can say that first argument to the jidal.warp function is the destination name or destination data set. If you have already created the data set, but when you are going to create the data set, you must know like what will be the extents, like what will be the width and height. So right now actually we have not created the data set, so we are just giving the destination file name only. So let JIDAL itself calculate all these things. Then the second argument is source data sets or source, like this second argument can be an array of data set objects or file names. So here also you can specify the directly data sets or directly file names also you can specify, though actually we have opened the files for reading as well and we have read them as data sets, so we are passing the data sets. Then you can pass many more arguments to the jidal.warp. Actually if you want to know about the options, you can check this jidal.warp options. So like these are different options, like you can specify format, output bounds. You have specified in which SRS, resolution of the mosaic image and so on. Like this you can go through this warp options. There are multiple options available. So anyway, we are not exercising any of these options. We are just exercising the default options. So like I have done here dst_ds jidal.warp mosaic image.tif and file names, and this I have specified the format, because Anyway, I have written is file names extension is already written as tip, so even I need not pass this formats argument. So let us see how it does. So this will be mosaicing all these file names. Anyway, we are passing the directly file names. I could have passed this ds_list as well here. So both options are available. I can say ds_list. And if then it creates a mosaic of all these data sets together and saves that in a image named mosaic_image.tif. So now if you see here, a file with mosaics_tif must have been created. So a file with name mosaic_image.tif got created. So now let us visualize that image. So this image can be visualized. Either I can either I can open this mosaic_image.tif, or actually jidal.warp returns the image also as a data set. So I am directly using this destination_data set was created by the jidal.warp. Now for visualizing this dst_ds.read as array. Now if I see this, so now you can see that like these are visible. So this is our 4 images. Actually this is not, I like you are able to, we are able to discern these, because these, it looks like this is not a seamless mosaic. Looks like, look, this area has a different contrast than this area. But so by improving some more options or applying some more image processing operations, we can make it as a seamless mosaic. So here you can say these were our 4 images. Like this was this first portion, and this has come beyond this. So this has come in this portion, and like this area has come to the left, top left. So this area looks like on the top left. So this area is on the top left. So this way you can create a mosaic of images using jidal.warp. Then if like you want more options to be exercised, then you can pass to this jidal.warp multiple jidal.warp options. So this way we can create a jidal. Actually one more thing is there, like suppose if your input images are overlapping, then what does jidal do? Jidal overwrites this overlapped area with the file which is coming last in the sequence. So but the requirement may be sometimes you may be willing to, suppose if you for the overlapped area you may be willing to do some operation there, like take the average of these, or like take the minimum or maximum of those, or maybe standard deviation of the overlapping area. But jidal doesn't have those options. So if you wanted to do image mosaicing like this, then you need to explore some other tools for that. So if you are using jidal and the areas of the images which you are mosaicing together, if there is some overlapping area, in that case it will put the last file which is coming in the sequence in that mosaiced image. So once this is done, we can just close this plot, plt.close. Now let us see how do we do some local analysis on an image. Local analysis work on 2 or more images or arrays that are the same size. Anyway, when we are working in a local way, so both the images must have the same size, and an algebraic equation is applied to each set of pixel locations. So suppose whatever analysis or equation you are applying to, that will be applied separately to the each pixels instead of applying it on the entire image. So so local analysis means whenever you are applying, so you may be applying some operation, like maybe you are calculating some index, like, or you wanted to add something to an pixel or subtract something from a pixel. So what will happen in case of local analysis? The algebraic equation whatever you are applying will be applied to each pixel individually. So one common task, like suppose if you see, one common task using multispectral imagery is to compute various indices, right? So if you are working in remote sensing data, so one very common task people will do is they will be calculating some indexes, like maybe NDVI or NDWI or any other index. So the indexes may be like such as you are writing a task for distinguishing between burned and unburned land. So by applying some indices, we can identify like this area has been burnt or this area has not been burnt, or maybe you may be measuring nitrogen contained in vegetation. So similar way, like you can measure the greenness by using the NDVI. So NDVI is called normalized difference vegetation index. So NDVI is a simple index that uses red and near infrared wavelengths to produce a number that ranges from -1 to 1. So NDVI is the index that is based on the some calculation that is derived from the red and near infrared wavelengths, and that it produces a number that comes in the range between -1 to 1. So the growing plants use a red wavelength for photosynthesis, but they reflect near NIR radiation. So a high ratio of these two measurements can indicate photosynthetic activity and healthy vegetation. So whenever you are using the ratio of these NIR and red, and if you are getting the number in range of 1, so that it represents a healthy vegetation, right? So when you are seeing the NDVI of an image, if you are seeing the values in the higher range like 0 to 1, so that means that those are so some photosynthetic activity is taking place in those pixels, or they may be some, or maybe indirectly you can say that this is some healthy vegetation. So this is like how do we do some local analysis. So like this was our first image, like 1 2 3 4 5, and these are the pixel values in the second image. Now if you are applying some operation or maybe some algebraic equation like plus minus or something, then it will be applied to the each set of each individual pixel separately. Like if you apply these operations, so 1 plus 1, so 2, so similar with 2 plus 2 4, so on. In every individual pixel the operation will be applied. So this is called a local analysis. So here we are not looking globally at an image, we are just looking at individual pixel level. So now let us see how do we calculate NDVI from this resource set to list 3 image. So this is the formula for this is like how do we calculate NDVI index. So NDVI is equal to reflectance is NIR minus red divided by NIR plus red. This equation must be applied to every pixel of our image. So now suppose if you want to calculate by applying this formula, NIR minus red divided by NIR plus red, but this operation is local, means this equation will be applied to every pixel in our image separately. So similar thing anywhere, this is the same thing. I'm just changing my working directory to this. Now here I have two different images like green band. So band 2 is green band and band 3 is a red band, and band 4 is NIR, and band 5 is SWIR. So I am just assigning the names of these files to these variables like green image, red image, NIR image and SWIR image, because I know that band 2 image is green, band 3 is red, band 4 is NIR and band 5 is SWIR. So that I can just write formulas like this green image minus red image. For sake of the convenience, I am assigning the names of these files to some variables which make my program more readable. So I have assigned to this. Now I will read one by one all of these images. Like suppose if you wanted to calculate NDVI. For NDVI we just need red and NIR images. So I am first reading this red image and assigning it to the variable called red underscore ds. Then similar way I am assigning it to NIR underscore ds to the NIR image. Now let us visualize or see that how this red band data looks like. So like I will say this red underscore band is equal to, now if I call, I will be fetching the band 1 from this red underscore ds. Now I will call red underscore ds dot get raster band and passing it the argument 1. So I just wanted to fetch band 1 from my red underscore ds. Now I just wanted to see like what data type the pixel intensities are stored in. So for that, like suppose if I visualize this image will be looking something like this. plt.im show. Okay, we will see visualize later. So here the next thing what I am doing, I am just checking what is the data type, in which data type the pixels are stored for this particular image, whether they are 16-bit integer, 32-bit integer, or floating point numbers or something. So why I am checking it? Because it may have some impact on my result. So let us see how it is. So if I fetch the NIR band, so it says that the data type of the image is unsigned 16-bit integer. Okay, so what will happen now? Suppose in this the data is delivered in unsigned 16-bit integer. Now suppose if the other image, like if my red image also is in the same 16-bit unsigned integer format, then if I do so actually if I see both of the images are stored in unsigned 16-bit integers. Now actually what I have to do, I have to apply some minus operation on these two images. Now suppose if you know, if I apply minus operation on two unsigned integers like a minus b, and if a is less than b, like suppose if I am getting the result in negative, so actually if I apply an operation on the unsigned integers, the resulting number also will be an unsigned integer only. So like if I am applying a minus b, and if the result of a minus b is a negative number, now suppose if I am going to represent a negative number as an unsigned integer, so it will be shown as a, because the in negative numbers the sign bit will be 1, right? So but our Python will interpret it as an unsigned integer, the resulting operation as well. So then it will be showing it as a large integer. So for avoiding that, we will be converting these unsigned integer. We need to convert, because whenever we are applying a minus operation, and we expect that the result may be negative also sometimes. So in that case, what we need to do, we need to promote these unsigned 16-bit integers to maybe signed 16-bit or signed 32-bit integers instead of, so because the operation of minus, sometimes we may get negative result also. Now suppose if we are sure that we will be always be getting the positive, like result of a minus b supposed to be, it is always positive only, then we can directly apply on the, we need not change their data types. But now if we expect that the result may be negative as well, so if we do a minus b on two unsigned integers, so the result is coming as negative numbers, in that case the sign bit will be 1, and because the Python will be interpreting it as an unsigned integer only, so it will be show a large number. So because of this reason, we are first converting the data type of these two images from unsigned 16-bit to 32-bit signed, or actually we could have converted it to the signed 16-bit as well. So that also might have served the purpose, but for better we are just converting it to 32-bit signed integers. So first thing what I am doing, red band dot read as array. So from that red band we are reading the entire array and converting to dot as type np dot int 32. So every pixel's intensity data type we are changing from unsigned 16-bit integer to signed 32-bit integer. So same thing is done for NIR band as well. So once this is done, now if I see the data type of this red dot d type, it is 32-bit. int 32 means it is signed 32-bit integer. Now for calculating the index, now we can apply directly the formula, right? Like what was the formula for NDVI? NIR minus red divided by NIR plus red. These NIR and red are arrays. If you are doing it in other programming languages, then you need to write loops. But in case of NumPy, we can just write it as like what we are doing in a simple variables. We need not write any loops. So it will be calculated this on element wise. So this will be so this formula will be applied to each pixel or each cell in our array. So NDVI will be NIR minus red divided by NIR plus red. So now let us visualize this NDVI image. So now same thing only, plot dot figure and color map, we are giving it a gray color map, and I am attaching color bar also to it. So now if you see this, so now you can see that the color is ranging from somewhere, maybe this may be some -1 to +1. If I see this image in another box, so you can see here, like the areas where very healthy vegetation is there are shown in bright color or bright intensity are shown as white, and the areas which has less vegetation, or you can see that these water black areas, so these are shown in the dark color. So this way with NDVI we can extract like where all there is vegetation or healthy vegetation. So depending on, you can make the, so this way you can calculate the you can generate NDVI image from your image by using just few line of code using GDAL. So now similar way, let us see the calculation for NDWI. So NDWI finds pixels which contain water. So for the formula, NDVI is calculated using green and NIR band. So NDVI equal to green minus NIR divided by green plus NIR. So this also will give you the results in range from -1 to 1. So the water pixels which contain water will have the value maybe above 0. So maybe above some like above 0.2 or 0.3. So that threshold actually, after seeing the image, we must decide. So let us see how do we calculate NDWI. So NDWI also can be calculated in the similar fashion. So same thing, like here I am calling this all these steps I am combining in just I am just combining this, I am what you call chaining multiple functions call all together. So in the previous case we were calling like GDAL.open, then .read as array, then converting as type in different steps. So here all these function calls are chained together. So one by one we are calling here like GDAL.open green image, then read as array, then convert is type to in 32. Similar way for NIR, actually NIR was already there, but anyway it is done. Then next, like NDWI is equal to green minus NIR divided by green plus NIR. So if I do this, and let us see that how the image looks like. So now you can see that the areas where the chances of pixel or water pixels are shown in the bright color. You can see like this is a Nainital lake. This is now shown in very bright color. So actually now suppose now your requirement is like you just wanted to extract just water bodies from your image and mask all other areas. So now you first need to choose some threshold, like okay, above this threshold these may be water. So by looking these, so let us say that now we have chosen that NDVI above 0.1 we want. So now we just want to keep only those pixels where the value of NDVI is above greater than 0.1 and mask all other pixels. For that, like in NumPy lecture I explained, there is a function called np.where. So with this NDWI equal to, we are saying np.where NDWI is greater than 0.1, retain the value in that pixel, or we can say that make it 1 and all others make it 0. So now if I see the image, you can see that only this. So this way we were able to extract to some extent a water body. Actually some things are missing anyway, so we need to lower the threshold, like if these were also water pixels, so this may be a river bed, but may not be exactly water pixels. So this way you can just extract a water body from here, but here is one manual step is involved. You need to choose the threshold, like okay, I need to, so NDVI above this threshold only are the water pixels. So this way you first need to choose the threshold. So this and then you can, so this choosing the threshold is a bit tricky. So this way you can extract the water bodies from any remote sensed image using NDWI. So then there is one more index that is called NDBI, or Normalized Difference Built Up Index. So NDBI is useful for measuring the presence of urban buildings. So suppose if in your image you wanted to check for the presence of urban buildings, so it can be calculated using shortwave, infrared and near infrared bands. So NDBI can be calculated using SWIR and NIR bands. So the result also will be, anyway, this will be range from -1 to 1. So where low values of NDBI represents the urban land and high values, so no low values of NDBI represents no urban land, means these areas there is no urbanization of those pixels. And if you see the values of NDBI above 0, so that maybe those areas are urbanized areas. So the formula will be like SWIR minus NIR divided by SWIR plus NIR. So same thing like in the same image, if you see, so NDBI, so you can see that areas where the value of NDBI is above threshold, so those are only maybe the urban lands, like these areas you can see. So the threshold may be a bit higher. So these areas, so these are some area in Haridwar. So these are the urban areas in Haridwar. So this way, by using NDBI, you can identify the areas which are urban in your image, or that this way you can find like how many pixels in. So you can do some classification, some elementary classification, like okay, and if we first calculate the NDBI for your area, and thereafter you can calculate some statistic like okay, in this area these many pixels are of urban. So or suppose if you want to check, you are checking the time history, like okay, in 2013 these many areas were urban, these many pixels were coming in urban. In 2016 these many pixels now are coming in urban. So this way you can check the growth of urbanization or anything like this you can do with this NDBI index. So you can do some statistical calculation on your image. So this was all about local analysis. So this way you can do any kind of analysis on your image just by using few commands. So now let us talk about global analysis. So local functions were working on every individual pixel. So they were not working on the entire image. So global functions work on the entire image, such as suppose you are doing some proximity analysis or cost analysis. So a proximity analysis determines the Euclidean distance of each cell to the nearest cell that is marked as a source. So suppose now you have an image that contains the water bodies. Right? So some water body or some river is there in your area, and you have an image in which you have marked them. Okay, these pixels are water bodies. Now suppose if you wanted to calculate a proximity map, like for each pixel in your image, how far it is from the nearest water pixel. So here what we are doing, for every pixel we are checking for the entire water pixels and checking which is the nearest water pixel from that particular pixel. So instead of doing some operation on an individual pixel, we are doing that or searching that or applying that operation on the entire image. So that is called global analysis. So here the proximity analysis is determining the Euclidean distance of each cell to the nearest cell that is marked as a source. So in our case, like suppose if you are checking for the proximity to the water source, maybe so here what we are checking for every pixel, we wanted to know like how far or what is the word, which is the nearest pixel for it. So here the source pixel will be all the water pixels. So for each pixel we are determining which is the nearest water pixel for that particular pixel. That will be our target pixel. Or so anyway, this is the same thing. So here we are using a data from Global Surface Water Product from the European Commission's Joint Research Center. This data set is based on the Landsat 5, 7 and 8 imagery, and it describes the occurrence, change and seasonality of surface water from year 1984 to 2020. So out of this we have used two layers here. one is the water extents layer. So this is the maximum water extents, provides the information on the all locations ever detected water as over 38 years of period. So by analyzing the Landsat 5, 7 and 8 images for last 20 or 30 years, so they have created a surface water map. So in that, this water extents map shows like the pixels, if it is showing only all those pixels where in last 38 years, if any time it was a water pixel, so that pixel will be shown as like maximum water extents. So in last 38 years, if in any of those images, if that pixel contains water any time, so that pixel will be marked as water pixel. So then there is another layer called seasonality. The seasonality map provides the information concerning the intra-annual behavior of water surfaces for a single year. And like it shows like this pixel was permanent water. So in this pixel always there was water present, and maybe like this pixel 10% of the time water was there, 90% it was not there, or maybe 30% time water was available there. So this way we can identify the pixels. Like this way we can identify the seasonal water bodies. So there are two levels, two images, water extent and seasonality. And let us do some proximity analysis on these two images. So anyway, these are all the same. So there are two images. I have water extents.tif and seasonality.tif. So we'll be reading those images one by one. So DS water, we are reading the water extents image, and seasonal image. I am just storing them in a dictionary just for easy access, may not be important for this. Now let us visualize these images. How do these images look like? So if this is just for visualization, this is not important here. So now if we see these images, so like this is the water extents image. So it shows that these all pixels contain water, like last 38 years data if we analyze. So these all pixels, these are the pixels which contain water at least one time in that 38 years. So this is what we call maximum water extent. And this image is showing like when all the seasonal water, like if you see the colors which are in dark blue, so these are permanent waters. So these pixels contained always water. So these were permanent water pixels, and like these pixels which are shown in the light blue color. So these are seasonal water pixels. So they may be like these pixels contained water only maybe during a rainy season or some other season. So these are the seasonal water pixels, not permanent water pixels. So for calculating the proximity, we will use the JIDAL proximity tool. So the JIDAL proximity tool generates a raster proximity map indicating the distance from the center of each pixel to the center of nearest pixel identified as target pixel. So for example of this example, so suppose this was our original image, or so here every water pixel is what we call is a target pixel. Now for this, like this in this image, so there are so many pixels lying here. So what we will do, we will calculate, like so for example we are calculating the proximity to the water. Suppose if you want to calculate for like, then what we will do, for this pixel we will calculate the distance of a water pixel which is nearest to it. So this way we will create a map. So this way we can create a map, like suppose if you want to we are doing a project for some, like where do we have to install the water supply tank so that the entire city can be served water with minimum distance. So that this type of map, suppose if we wanted to generate, so we can use proximity analysis. So for this we will create a proximity map. For every pixel in our area of interest, we will calculate the distance to the nearest water pixel. Like for these pixels, this particular pixel may be the nearest and distance may be less. Like for this, the pixel lying in this area, so this water pixel may be nearest. So this way we will create a proximity map, or surface water proximity map, you can say. Let us see how do we do that. So here we want to find the points which are closer to the surface water, or in other words, maybe we want to create a proximity to surface water map for some of our application. Maybe like suppose we are going to we want to build some houses near this water body, so that we will create that, okay, at least in last 38 years the water has come at least to these regions. So we will create a map, okay, at least our houses should be beyond these locations. So suppose this kind of analysis if you wanted to, or depending your analysis you can choose. And let us see how do we do the proximity analysis. So first thing, anyway, for that we need to create an output image. So an output image is created like destination dataset, create copy proximity.tif, and we are copying because this output image needs to be same as this our water image. So all the extent, projection, everything is getting copied from there. So we are calling the create copy method, tst.create copy. Then this will be our source band. Source band will be our water band, and proximity band will be our what we are getting in the raster data set. And this is not required here as of now. Now how do we calculate the proximity? So proximity will be called jidal.compute proximity, jidal.compute proximity, and your source raster, like in which contains your target pixels. Like here our target pixels are the pixel which contain water. Then this is our output image. So proximity band, and the distance, like distance what you want to use, whether you want to calculate the Euclidean distance between the source pixel and the target pixel, or you wanted to calculate the distance in terms of how pixels far it is from the source. So either you can say in the Euclidean distance or pixels. Suppose if you want to calculate in pixels. So this has generated a proximity map and stored it in the in the proximity band. Now let us read and visualize this image. So proximity band dot read as array. So this proximity band I am trying to reach, and this way you can see that the areas which are very dark in this visualization, dark points are points that are closest to the surface water. So these points which are shown in the dark are the points which are very close to the surface water, and the points which are lighter green are far away, and these are the much farther, these are shown as white color. And this is the scale. You can see that these many pixels. So blank points or all white are further than max distance. Actually later on we can see that we can specify another argument called max distance. So max distance means, like suppose if you want to say that the pixels which are above certain threshold, like pixels which are more than 100 pixels away from this pixel. Suppose all these pixels we wanted to show as some white color. So in that case we can pass it another argument, like while computing the proximity we can specify like max distance. So what does this do? Like if the max distance is above, if the pixels distance to the nearest water pixel is above 100 pixels, so then that will be shown as a white pixel. So this is like compute proximity. And now here we are showing both these plots together. So like here you can see that this was the original, and here we have defined like all the pixels which have distance greater than 100 pixels to be shown as white. So this way we can create two types of graphs. So here actual distance is shown here, but here the max distance, like distance above 100, is shown as completely or blank pixels or white pixels. So this way we can create a proximity map using Jidal proximity tool. So similar way we can calculate for the seasonal water also. Same thing we are doing here. So this shows a proximity map for seasonal water. So even for seasonal water, these pixels are the pixels which are nearest to the water, and the pixels which are shown as blank or white, these are farther away or more than specified distance, more than 100 pixels. So similarly, like you can calculate for here we have calculated distance in terms of number of pixels. Then later on you can calculate distance in terms of Euclidean distance between these two pixels. Now let us do some DEM processing. So like the digital elevation model or DEM shows you the surface elevation of every point in your every point on the surface of the earth. So GDAL DEM, like from the DEM actually there you can derive multiple byproducts, or what you can, like you can suppose from the digital elevation model, suppose if you wanted to derive the slope of your terrain, or maybe you just want to create a hillshade map of your terrain, or you want to calculate aspect ratio, whether the northern aspect or southern aspect is there in, or like what is the direction of the slope in your image. So suppose if you want to do all these type of analysis, so GDAL DEM is a utility that enables the user to apply different processing on a digital elevation model. So there are different, you can apply different kind of processing on a digital elevation model, like you can create hill shading, and you can calculate slope and aspect. Slope means what is the slope of the terrain, and aspect is like in which direction the slope is, northern or southern. Then you can calculate terrain ruggedness index, or TPI, topographic position index, roughness. So anything what any derived parameter from anything which can be derived from the DEM can be done using GDAL. So first let's see how do we create a hill shaded map. So hill shading creates the shaded relief raster from the DEM. So suppose if you want to create a shaded relief raster from the DEM, you can create it using GDAL. So how the shaded relief map is created? So this works by, so it just tries to simulate a light source that would be at an infinite distance and whose direction is by default at upper left corner of a raster with an altitude of 45 degree. So here we are simulating a light source that is at infinite distance and whose direction is to the 45 to the top left upper left corner of the raster with an altitude of 45 degree. So shaded relief, also known as the terrain shading. So it is a clever way to make contour maps appear more three-dimensional. Suppose if you have created a contour map and you wanted to look it appear as a three-dimensional view, so that you can clearly prominently see the features like ridges and gullies over your area. So if you want to see these features prominently, then you can create a hillshade map of your area using the DEM. So let us see how do we create a hillshade map. So this is a digital elevation model I have available. This is the ALOS Pulsar derived digital elevation model. So for creating the hillshade from this, you need to call on this. GDAL has a function called GDAL.DEM processing, GDAL.DEM processing, and this argument you need to pass first your output file name, then output or destination file name. So suppose this I want to save in a hill.tif file, then your input data set, that is DEM, and which processing you want to apply on that. So I wanted to create a hillshade map or shaded relief raster from this. So I will depth processing equal to, I will pass it the argument hillshade, and output format I wanted to be in geotiff. So with this it will create a file with name hill.tif. It must have created here. So hill.tif file got created here. So now suppose if I want to see this file, so I will call it, I will just open this file for reading. And suppose op.read as array, if I open this hill.tif file, so this way you can see that all the ridges and these things are quite visible. This is a like contour map. It looks a three-dimensional view. So this way you can create a hill shaded map. So for visualizing your terrain. So similarly, suppose if you want to calculate slope from the DEM, so same thing like this, and same DEM and GDAL.DEM processing, and here processing is equal to, you want to put it as slope. So then I am reading that, and by default what is it? It was minus 9999 as the no data array. minute out slope.tif. So I'll just read that file. So this is the slope map. So similar way you can calculate the aspect. So here you need to pass the temp processing as equal to aspect and calculate the aspect map. And suppose if you want to calculate the sine of this, you calculate the aspect map. So this way you can calculate the aspect map. So here you can see that you can you know the aspect of your slope as well. So this way you can, using GDAL, you can calculate, you can do any processing on your DEM. So this was all about today's lecture. So just a quick review, like what did all we explain today. So first thing we did with GDAL was creating a mosaic. So suppose we have two or three, four images of some area and we wanted to combine them together. So we can combine them using GDAL.warp utility. So with GDAL.warp we can create a mosaic of images. Then we discussed about how do we do some local processing on the local analysis on an image, like where some algebraic operation or any operation that will be applied individual on the individual pixel. So next we talked about global analysis, where our analysis, like every pixel, what operation we were applying, the operation was applied instead of a single pixel, it was applied based on analysis of the entire image. Like we did the proximity, we calculated the proximity map, like for every pixel we calculated from the entire image which is the nearest water pixel for that particular pixel. So we created the surface water proximity map. Then we discussed about DEM processing, like how do we create different products from digital elevation model, like hill shading map or slope or aspect. So this is with this we come to